Earth's history isn't just a story, it's a tangible record etched into the very rocks beneath our feet. Layer by layer, over billions of years, these rocks have been accumulating, preserving a chronicle of our planet's evolution. Each stratum whispers tales of ancient seas, long-lost continents, and dramatic shifts in climate. Sedimentation is the fundamental process at play, where particles like sand, carried by wind and water, and mud, along with other organic and inorganic materials, gradually settle and build up, often in bodies of water like lakes and oceans. This deposition is a slow, continuous process. Over vast stretches of time, the weight of overlying sediments compresses these materials, eventually forming these distinct layers of sedimentary rock. Each layer is a snapshot of a moment in Earth's past, a frozen frame in the planet's long and dynamic history. These layers are not just made of sediment, they also capture ancient environments and life, preserving fossils of plants and animals that once thrived on Earth. The law of superposition, a cornerstone of geological science, helps us read this rocky story, providing a framework for understanding the relative ages of these layers. In undisturbed layers, meaning those that haven't been overturned by geological forces, the oldest layers are at the bottom, representing the earliest period of deposition. Conversely, the youngest layers, representing more recent times, are found at the top. It's a simple concept really, like stacking newspapers or books. The first ones you put down are always at the bottom, and the most recent additions are on top. Geologists use these fundamental principles of sedimentation and superposition, along with other dating techniques, to piece together the sequence of events that shaped our planet, creating a comprehensive geological timeline. By studying the composition and characteristics of rock layers, we learn about shifting climates, from ice ages to periods of intense heat. We can also understand the forces that have shaped the Earth's surface, such as the uplift that creates rising mountains. And of course, we gain invaluable insights into the history of life on Earth, tracing the path of evolving life through the fossil record. The rocks are Earth's autobiography, a multi-volume set filled with incredible stories. All that's needed is the knowledge and curiosity to start reading and waiting to be read. With sedimentation and the law of superposition as our guides, we can travel back in time, exploring ancient landscapes and ecosystems. It's a journey through deep time, and no time machine is required. Science, particularly geology, lets us unlock the secrets of our planet's past, revealing the forces that have shaped the world we inhabit today. Let's look closer at how these layers form. Rivers act like conveyor belts, carrying mud, sand, and pebbles from land to lakes and oceans. When the water slows down, like entering a calm lake, it drops its load of sediments. Gravity pulls the particles down, with heavier ones settling first. Over time, these deposits build up, creating new layers on the riverbed, lake, or ocean floor. Each flood, season, or sea level change can create a distinct layer. Layers vary in thickness, color, and sediment type, recording environmental changes. These layers are like tree rings, but for entire landscapes. They reveal the history of environments over thousands or millions of years. Sedimentation is nature's way of archiving Earth's story. Nature doesn't just pile sediments randomly, it sorts them by size, shape, and density. Fast water carries big particles as it slows. The heaviest drop out first, then sand, then fine silt and clay. This sorting tells geologists about the energy and environment where each layer formed. Well-sorted layers mean steady currents, mixed layers suggest sudden changes. Particle shape and weight also affect how far they travel before settling. Through these processes, nature creates distinct, organized layers for us to study. Each layer is a clue to the conditions of Earth's past. With these layers of Earth's history carefully placed over millennia, how do we begin to decipher their intricate story? How do we unravel the secrets held within these ancient formations? Enter the law of superposition, a cornerstone of geological understanding. Nicholas Steno, a brilliant 17th century scientist and a pioneer in the field of geology, realized a fundamental truth. In undisturbed rock sequences, the oldest layers are at the bottom and the youngest are at the top. This simple yet profound observation provides the key to unlocking the relative ages of rock formations. This principle is the very foundation of geology, providing a framework for understanding the timeline of Earth's past. It's like reading a book from the first page up, with each layer of rock representing a page in Earth's grand narrative. Each layer marks a distinct period in time, a snapshot of the Earth's environment at that moment. This allows geologists to determine the order in which events occurred, piecing together the sequence of geological history. Steno also gave us the principle of original horizontality, another crucial tool in our geological toolkit. This principle states that sediments are usually deposited in flat, horizontal layers under the influence of gravity. Therefore, if we observe layers that are tilted, folded, or otherwise deformed, it indicates that something significant happened after they were initially formed. This could be a dramatic event like mountain building, driven by immense tectonic forces. Furthermore, we have the principle of cross-cutting relationships, which helps us determine the relative ages of geological features. This principle states that geological features like faults, which are fractures in the Earth's crust, or intrusions, where molten rock forces its way into existing formations, are always younger than the rocks that they cut across or penetrate. And then there are inclusions. These are fragments of older rock that become embedded inside a younger rock layer. Logically, these inclusions must be older than the rock layer that contains them. Finally, lateral continuity suggests that rock layers originally extended outwards in all directions, even if they are now separated by erosion or other geological processes. By applying these fundamental principles, geologists can begin to reconstruct Earth's dynamic and ever-changing history, revealing the secrets hidden within the rocks beneath our feet. The Earth's history is etched in stone, layer upon layer. These layers, primarily sedimentary strata, hold clues to the planet's past, like pages in a vast geological book. These principles form the backbone of stratigraphy, the study of rock layers. It's a fundamental discipline in geology. Stratigraphers are Earth's detectives, meticulously piecing together the story of our planet. They begin by examining outcrops, exposed rock formations that reveal the hidden depths below. Then, they move on to measuring layers, carefully documenting their thickness and composition, and identifying rock types and fossils, which serve as crucial markers in the geological record. Fossils and layers help date rocks, providing a relative age for the surrounding strata, and reveal ancient environments, painting a picture of past climates and ecosystems. Correlation is key, allowing geologists to connect disparate rock formations, matching unique layers like volcanic ash, which spread rapidly across vast areas after eruptions. Across regions connects distant histories, creating a cohesive narrative of Earth's evolution by linking layers and understanding their relationships. Geologists build a global timeline of Earth's changes, a chronological framework for understanding our planet's past. Geological maps show the types and ages of rocks, providing a visual representation of the Earth's surface. At the surface, revealing the underlying geology, guiding exploration for resources and hazard assessment for potential geological risks. These maps reveal the structure of the land, the arrangement of rock formations and geological features, and help locate resources such as minerals, oil, and gas. Stratigraphy provides the framework, the essential foundation, for understanding everything else in geology, from plate tectonics to the evolution of life. It's how we reconstruct ancient landscapes, envisioning the world as it once was, and climate shifts, deciphering the evidence of past environmental changes. Mapping Earth's layers is a complex and ongoing process, is the foundation of our knowledge of the planet, providing insights into its past, present, and future. Why does all this matter? Because understanding rock layers shapes our world today. Archaeologists use these principles to date artifacts and uncover human history. Paleontologists rely on stratigraphy to trace the evolution and extinction of life. Engineers study rock layers before building to ensure safety and stability. Ignoring geology can lead to costly or dangerous mistakes. Mapping sedimentary layers guides the search for oil and gas, coal, and groundwater. Geologists use stratigraphy to find resources that power our lives. From ancient secrets to modern needs, sedimentation and rock layers are fundamental. Science isn't just about the past, it's about building a better future. The story of rocks is the story of us all.